Okay, let's move on to the focus part of the first morning session. I'm very happy to welcome Hans Hepach, who is working on his doctoral thesis in Vienna at the Institute for Quantum Optics and Quantum Information. So he studied originally in Germany, so I give you a little background, and then an Erasmus brought him to Vienna where he got stuck, is my understanding, working in the group of Markus Aspelmeier. And he's been crucially involved in experiments on tiny, tiny masses. So he's an experimentalist. And he's been, well, he takes a crucial role in preparing, in making these very, very ambitious experiments for smaller and smaller masses. And that's also what he's talking about today. And I'm also very grateful that at very short notice, he's agreed to step in for Aspelmeier, who was originally planned to talk here, but I'm sure he'll fill his feet happily and very expertly. So thank you very much.
Thank you very much for the introduction. So I'm a PhD student with Markus Aspelmeier in Vienna. And so first off, I need to apologize on behalf of Markus that he couldn't be here. He really wanted to come, but in the end it didn't work out. So let me quickly start by saying what we are actually doing in Vienna in our group. So the main question, or the main focus of our work is designing and performing experiments at the interface between gravity and quantum mechanics. This part, or these questions are actually pretty old for our field, let's say, as these questions have already been discussed in the 50s. So I'd like to start off with this quote from John Wheeler, who said that it is the challenge of checking whether gravity actually extends to smaller and smaller masses cannot be evaded. This is a quote he made at the 1957 Chapel Hill conference, where two of the most prominent questions that were discussed were, do gravitational waves actually exist? And on the other hand, do we need a quantum description of gravity? I think the first question, so whether gravitational waves actually exist, has been quite well answered now. But the question of, or the experimental verification that we actually need a quantum description of gravity is still outstanding. And this is where our focus lies. If we go on to answer this question, there are two possible approaches to the problem. One is, well, we can just assume that there exists some quantum theory of gravity and then just probe its low energy consequences. Or on the other hand, we can assume nothing about how this interplay actually works and just, well, probe the quantum configurations of gravitational source masses. There are two main differences between those two approaches. The first one is, if we assume that there exists a quantum theory of gravity, we don't necessarily need to actually measure gravity. So there's no need for actual gravity measurements, whereas in the second case, we actually do need to measure gravity. So in a sense, the second approach, although it doesn't assume anything on the theory part, it is much more challenging in terms of actually experiments, and it is the approach that we are focusing on currently. So we just heard a little bit about gravitational cat states, which is the overall goal of the experiments we are currently performing, although we are still quite far from actually doing those. But there are two possible, at least as far as we can see, there are two possible implementations of such an experiment. Both of them require large quantum states, but the difference is that in the one hand side we have two large quantum systems or quantum states in the sense that their extension, their wave function is actually quite extended, and in the second possible way we have two superpositions which we want to couple gravitationally. In both cases, the entanglement rate between those systems is the same, and I just want to stress here that the generation of such an entanglement via gravity is obvious from a quantum from a quantum perspective, but not so from the GR perspective. So why hasn't this experiment been done yet? The important part here is this entanglement rate, where we have where the mass enters of the systems we are looking at, the size of the quantum state, the decoherence time, and the distance between both partners here. So for the quantum experiments, the first part here is the challenging part, let's say. So you need to have this large quantum state extension, and the decoherence time also is crucial here. And from the gravity experiments, this d, the distance, the center of mass distance between both systems, is what is actually difficult to achieve. You need to keep in mind here that the center of mass distance can't be that small, because you also have to deal with the extension of your object, let's say. So in our case, where we performed gravity measurements of 2 millimeter gold spheres, obviously the center of mass distance can't be smaller than 2 millimeters, because otherwise you would be inside each other in terms of the masses. So another way of looking at this is to look at this plot here, where the coherence times of quantum systems is plotted against the mass of the objects. So we have the metawave experiments, where we have quite long coherence times, but the masses are pretty small. The optomechanical systems we are also working on in the group, they have larger masses, but also smaller coherence times. And on the other hand, we have the gravity experiments, where coherence times up to now don't play a role, but the masses are much larger than for the quantum systems. So the question here is, for the quantum side, how big can we make the quantum systems without losing the quantumness, let's say, of the experimental constituents? And on the gravity side, the question is, how small can we make the objects without while still seeing a gravitational interaction between both masses. I've been working on the second one, so let me say a little bit more about the experiment we performed. The idea for the experiment is quite old now, so it is proposed in 2016. The main idea is to just take an object and modulate its position in space, and thus modulating the gravitational field it generates at the point of the source mass here. So, well, the proposal was for this kind of linear scheme. It kind of didn't work out, so we went further back in time and used a much older method of measuring here. So we decided on using a Cavendish-type rotational oscillator here, where we modulate the, we now have three masses. We have the source mass here, the test mass here, and, well, we need a counterbalance mass in order to keep the pendulum stable here. The advantages of such a system is that you are no longer susceptible to any translational motion that can occur by just walking by, or any kind of disturbance that occurs at larger distances than the separation of those two masses here. Yeah, so just a few key facts about the experiment. So the torsion pendulum consists of 2 millimeter gold spheres, which weigh about 80 or 90 milligrams. We have a rotational frequency of 3.6 millihertz, which means we have periods of 140, 160 seconds. The quality factor of our suspension is pretty low in this case, so a quality factor of 4 is nothing to brag about, but in our case it actually turned out to be a big advantage to performing the experiment here. The position of our source mass has been modulated by a couple of millimeters, so between 2 and 5 millimeters. Everything was performed at decent vacuum, 10 to the minus 6 millibar approximately, and at room temperature. So just to give you an idea of how this looks like actually in the lab, so we have our two masses here. We have a mirror underneath for detecting the rotational displacement of the pendulum itself. You can't see the suspension here because it's just too thin. And you also don't see the source mass because it's not in here. But you see the laser that is just shining on the mirror underneath the pendulum and is going to be recorded on a position sensitive detector outside of the vacuum chamber. Now, the main goal of the experiment has been to show or to isolate gravity as the main interacting force between both spheres. But in order to do so, you need to make sure that, well, gravity is actually dominant in your system, which is the biggest challenge in these kinds of experiments. First off, you need to make sure that the direct coupling between the source mass and the test mass is actually well under control. In this case, the most annoying part is the electrostatic coupling, as electrostatic forces are much stronger than gravity. In order to do so, we needed to discharge our pendulum to well below 100,000 charges, which sounds like a lot, but if you take into account that these spheres are about 2 millimeter in diameter, 100,000 surplus charges is actually pretty low. Also, you have magnetic coupling between those two. This is a magnetic spectrum we took at the place of the experiment. You see quite strong 10 millihertz lines in the magnetic field, the reason for which will become clear in a couple of slides. But you don't see these in the pendulum response, which is how we conclude that magnetic coupling is not a problem in our case. Then we have the environmental disturbances, which means, well, everything we couldn't pin down. This is seismic noise, this is people walking by, this is, anything you can think of. And the only, let's say, fundamental noise source that we need to compete with is the thermal noise of the suspension of the pendulum, which is this black line in the spectrum here. So we are sitting on top of the thermal noise in the quietest parts of the day. Yeah, so let me quickly say a couple of words about the discharge. Discharging of the pendulum. We borrowed our technique from the LIGO discharge method for their suspension and for their mirrors. It consists of using nitrogen, which flows over a set of high voltage needles where we produce ionized nitrogen, so positively and negatively charged particles. We then measure the ion flow to make sure that we actually have both polarities in there, and rely in the last part on a diffusion process in the vacuum chamber itself to neutralize any surface charges that we have in the system. Even though we achieve quite low surplus charges on the test mass this way, we still need a shield between both masses, so between the test mass and the source mass, because even though we have only 100,000 charges, electrostatic coupling would still be about an order of magnitude stronger than gravity without such an electrostatic shield, which also limits the center of mass distance you can achieve, because you need to account for something solid in between there. So what do we actually see? So if we take a spectrum of our pendulum, we see that we have our modulation frequency here at 12.7 millihertz. It's a quite strong signal in the rotational displacement of the pendulum. And we even see the first harmonics of this, which comes from the nonlinear form of the gravitational potential there. However, such an analysis here is not the best way to make use of the data we have, because actually the environmental conditions vary by about a factor of 10 here. So this is the same data as on the left-hand side, but with shorter intervals. So this is just 1 hour chunks of data, and you see that the overall noise flow varies by a factor of 10. But if you do such a spectral analysis, you actually assume a steady state of your system, which is not the case here, obviously. So the reason for this varying noise floor here is that we are situated right in the city. So we have two tram lines that go right here, the blue lines. We have two ones going here, the green ones, and another two, the red ones, and there is also a subway under construction right underneath the building. So obviously it's not the best way to perform such a precision experiment. And just to give you an impression of the annoyance of these factors, the gravitational field that is created by such a tram passing about 70 meters away from the experiment is on the same order of magnitude as the one we are actually measuring. So 70 meters sounds like a lot, but 90 tons is also quite a lot. Yeah. To further give you an impression how that actually manifests in the experimental data. So this is a seismogram. So this is not the actual data of our pendulum, but just the seismic movements around here. So first off, this is a timeline. So this is 1 hour chunks here, and the mean displacement of the size of the movement of the Earth. So first, what you notice is that well, it's much quieter in this part of the seismogram, which is just because it's during the night. Then, if you have a closer look here, where you see these little bumps here, they are quite regular, except for this one here. And this outlier here actually causes some problems because it delayed the identification of this noise, which is just the night bus passing by. Yeah, once we got that, we know that a spectral analysis of the data is not the perfect way to go about this. And to further stress this point, this is data of 1 weekend in the life of the experiment. So this is the well, already highly smoothed out version of the pendulum over the course of a weekend. So first off, we have these red periods where we actually performed work on the pendulum, on the table. So obviously the pendulum was excited there. Then during the night, you already see, well, it's quieter than during the day. That looks good. There is still something, well, this is you see also the difference between the weekday and the weekend before. There is something we don't know what it is. But you also see this kind of here. And this was the marathon, the Vienna City Marathon that was passing by, which is going just around the corner from the university. Yeah. So what did we do with the data we have? Instead of doing the spectral analysis, we actually performed the time domain analysis because we have the continuous time separation of both masses, and we have the force that is acting on the pendulum. When we do this, we can extract a coupling strength between both as the single fitting parameter here. And if we do that over the course of the measurement runs here, which is 3 weeks, you see that, well, it's varying still quite a lot, but we can say, or let's say we can reproduce the co-data value for big G within the range of our systematic error here. So this is the co-data value here, and this is the value we get. If you compare that to the usual like plots you see from the co-data group, our value would be well somewhere there. So well outside any range, competing with the current best experiments in precision determination of big G. Yeah. So I just want to say that although we have identified these as systematics, we have not corrected for any of them because that would have been too difficult in our case, and the only goal of this experiment was actually to show that gravitational interaction between such small masses can be isolated. So how do we go on from here? So there are two possible ways. One way would be to decrease the distance between both masses, and the other one would be to decrease the mass itself. I'm working on the decreasing the mass route. There's a second experiment being set up right now, which goes the distance route here. So just for size comparison, this is the current source and test mass, and this is going to be the source mass we are working on right now, which is on the order of a Planck mass. To do that, we moved the whole experiment to a mine, which is about 80 kilometers south of Vienna, where there's no subway and no trams and so on. And this is actually the best, or one of the best places to perform seismic and geomagnetic measurements in the world. So we are quite lucky to be able to move the experiment there. Now, to go on a little bit on the quantum side here, all those experiments I'm going to talk about right now are being performed in the group as well, and all of them merit their own talks. But just briefly, the main challenges from the quantum side is, well, that for the solid-state mechanical systems, they are large, which is good, but the coherence times is pretty small. On the other hand, you have the metawave interferometry, which have very good coherence times, but are limited in the size of the systems they can work with. And our goal is to use levitated optomechanics to, let's combine the advantages of both approaches. So one of those experiments is to measure the motion quantum ground state of a levitated nanoparticle, which has been done in our group in 2020 and before, where we achieved a ground state probability of better than 2/3. Another experiment which is going a similar route is to use a Kalman filter to control the system into the motional ground state, which we also achieved in this case. And the third route that we are currently setting up is to use levitated superconducting spheres to further increase the mass of our quantum systems, where we achieved pretty good preliminary results here in terms of the quality factor that we can achieve. So in essence, what we do is we have two approaches to tackle this question of designing an experiment for combining gravity and quantum mechanics. We have the bottom-up approach. Let's say bottom-up in this case means in terms of size, where we want to improve on the size of the systems where we can actually verify the quantumness of the systems we are working with. And on the other hand, we have this top-down approach where we want to show that gravity can be measured in the lab for very small objects here. So that's the group. Currently on the experiment for the gravity side, it's myself and Matthias who are working full-time on the experiment right now. For the Planck mass-sized object, we are pretty close to actually measuring something. So let's hope that in a year or two I can report back on those results. So thank you.
Yes, thank you for these fascinating insights into microgravity, or whichever way we might call it. Inviting questions, can we start with the online? Is there anything online? Questions that have come in? Yeah.
So there's one question on Zoom from Deepan Betal. He's asking, does cosmological expansion play a role in the coherence time?
The short answer is I don't know. Please keep in mind that I'm not, I really don't know much about the theoretical frameworks there. I'm more concerned with the experimental challenges, which are up to now big enough. Sorry.
There's another question. How do you characterize the quantumness?
for now, that's going to the motional ground state. So, yeah, being able to really show these correlations there.
So, Badri first had a question, and then.
You described the seismic noise in the system, and you described the moving of the experiment to a new site. Wondering, I missed the thing about seismic isolation. Would it not make some sense to, spend more time on the seismic isolation and try to improve the situation in Vienna? Is that feasible or not?
Yes and no. The problem with the seismic isolation in this case is that the frequencies we are dealing with are so low that the typical seismic isolation that you perform or that you do, for example, in LIGO, don't really apply there, because there the measurement band is above the isolation band, let's say, so you are relying on mechanical systems to be, well, far above their resonance, which means that if you want to measure something at millihertz frequencies, your resonance frequency of the suspension needs to be in the microhertz regime, which is very difficult to achieve. And also just keep in mind that for the quality factor of our system and the frequency we are dealing with, in order to measure or to really see the width of our peak in the spectrum, we would already need to measure for 3 months. And this is for millihertz frequencies. So for a suspension in the microhertz regime, that would be in terms of years, which is not feasible.
I had a double question. Thank you so much. A really nice talk. The first part was about why you did the experiment at room temperature and whether temperature control will add something. And then what sort of challenges you expect in the microgram version of the experiment.
So the challenge, let me start with the second question. The challenges in the microgram regime are pretty much the same as they have been before. The main part that permits us to perform these experiments in the microgram regime is the quality factor of our pendulum, which dramatically increased by just moving it. So this actually directly allows us to perform these measurements at the microgram regime. The first question about the temperature control is, well, yes, obviously we would benefit from performing these experiments at lower temperatures, but not as much as we would by optimizing other parts of the experiment. So temperature does play a role, but the scaling is just not worth the effort right now.
Okay, one final question over there.
Hi, I was wondering that in case of the Cavendish experiment, there was this screen that screens the different kind of interactions, but can it also screen the gravitational interaction somehow?
No.
Or at least modify it somehow, like,
Okay.
When you are moving it, it kind of dampens the effect that will go to the other side.
So the only way I can see how the shield actually influences the experiment itself would be if the shield itself is moving. So the important part here is to make the shield rigid and thus eliminate this possibility, which is, I think, what we succeeded in doing there.
Okay, well, thank you very much. Thank you very much to both speakers, by Locke and Hans, in this session. Before the applause, we reconvene at 11 o'clock sharp after the coffee. So thanks again.